Well, Alan and I got together yesterday morning to try to revive our memories in anticipation of this, and so we got down and tried to make a list of things that were done and who did them, and basically we were just thinking about the people at Ames. Many people used the Illiac that were not at Ames, of course, or the ARPANET and so forth, and even at Ames we really only had detailed knowledge of the people in Harv Lomax's branch or people who interacted with the Illiac through Harv's branch. So this leaves out a lot of very interesting people like John Warnock and so forth who worked at IAC. They had a tremendous amount of talent over there, but we don't really know what went on inside IAC, and we didn't at the time, and we often wondered. But so I'm going to kind of start chronologically, and I'll mention a lot of names here, and many of these people are actually in the audience. And if I mention your name, raise your hand so people can see you. You don't all have gray hair like I do. So I came to work for Harv Harv Lomax was the branch chief of CFD branch, which was established in 1971. And it was really established at the same time, roughly, that the Illiac that the arrangement was made with ARPA to put Illiac here rather than at University of Illinois. And it all kind of happened together, and Harv's first duty, his first item that he had to fulfill, sort of, was to make sure that when Illiac arrived, CFD codes were debugged and ready to run on the first day that that machine was ready to run them. So Harv, I guess, went out and looked at the language situation and so forth, see what was available, and found out that there really wasn't much available in the way of languages and support. So he organized a kind of a loose crew that was working on this when I arrived in '71, and Ken Stevens was a member of that, and Margaret Covert, who's I don't think here, Reese Sorensen, wherever you are, Reese, you're here, he was involved in that, I was involved. Yvonne Schaefer was involved, and we had a undergraduate co-op student by the name of Vernon McGeorge, and I doubt if he's here. If he is, raise your hand. No. He's probably a grandfather now. And Vernon was the only actual computer scientist on the whole crew. The rest of us were engineers and mathematicians. But at any rate, that was in the spring or early summer of '71 when I got here. And in the fall, Ken bailed out on us, went back to graduate school. And Harv kind of drifted off. He decided that compiler writing wasn't his thing, and he didn't know anything about it, and of course none of us did. And he drifted off, and basically it came down to Reese and myself. And we tried mightily to take, neither of us had ever written a compiler or anything before, so we tried to divide a job into two pieces with a clean interface in between, and each of us would do a half. And now you correct me if I get this wrong, Reese. Well, of course, what happened was neither of us knew what we were doing, so every day the interface had to change. And after about a week of this, we both got a little frustrated, and we went to Harv and said, look, Harv, this is a one-man job, you know, with no interfaces. And since I had the biggest mouth, Harv said, okay, well, you do it. So he let Reese off the hook at that point on the compiler. And so Vernon McGeorge and I went off and we moved the project that was running on an 1800, IBM 1800 at that time, which was Harv's own personal machine. We moved it over to the 360 running TSS and started coding in Fortran 4. And I basically designed most of the language to mimic Fortran. And one of the things that Harv was very concerned about was efficiency. We were concerned that people would run into Amdahl's law on this machine and they would start coding serial code, and of course the machine would just die. And so the decision was made to make it difficult for people to use this machine in scalar mode. And that was really a conscious decision, but as a compiler writer, it greatly simplified my life because it meant I didn't have to try to optimize serial code for a parallel machine. And so what we wound up with was a language called CFD, and this is the manual. It's not very thick, but that's all you needed to know to write a code on the Illiac. And we called it CFD because we couldn't think of any other name. It was the CFD branch. It was not very imaginative. But basically, I would say the language was somewhere between an assembly language and a high-level language. It looked like Fortran, and all the syntax and semantics were like Fortran, but the rules were very stringent about what kind of arithmetic expressions you could have in the CU and what kind in the PEs and things. So basically, when you got ready to compile this thing, it was essentially an assembly language. What was easy to write in CFD would compile into one instruction or two instructions or a small number of instructions. So it became very difficult. Anybody who wanted to misuse this machine had to write a lot of CFD code to get that thing to do scalar arithmetic and stuff. And that turned out to be a sort of a wise move for Illiac, but it essentially meant that CFD was not a general enough language to survive after Illiac's demise. And so when Illiac died, CFD died with it, which was a good thing. So a little bit about that compiler. It was written in Fortran 4, ran on TSS. It produced a binary object. We shipped the binary object over the ARPANET to the front end of Illiac, which was a PDP-10. We link edited it on the PDP-10 and executed from the PDP-10. Basically, you did a load and go. You just took that executable module that you had, loaded it into an absolutely bare memory, Illiac. There was no system memory, no system software running in Illiac at all. Everything was your code. And you linked it, loaded and go. And initial data, if you needed to load the disks initially with data flow fields, which we always saved at the end of runs, so to load initial flow fields or store computed flow fields, they had to go from Illiac disk to tape. There was no formatted I/O at all. And Ken had to jog my memory about how we debugged. I came here today and said, "How the hell did we debug? You know, I forgot how we debugged this code." He said, "Well, there was a hex dump. You could do DDT on a hex dump on the 10." That's the way. So that answered that for me. Okay. Well, I'll go a little bit further. Vectoral, which Alan will talk about, was the language that came after CFD and was a real language, and that lives on today, and he'll tell you about that. Supporting code for the Illiac, some of it was written by Dave Gallant. I don't know if Dave is here. He wrote the scientific subroutine package for the machine. I wrote a lot of subsidiary stuff, FFTs, transposes, disk I/O utilities, and so forth, and Alan wrote a lot of 32-bit algorithms for the machine. For those of you who don't know, the machine had 64 processors, each of which could handle operands of length 64, or you could run it as 128 processors with 32-bit operands, so each processor would split it down the middle. When the machine first came up, 32-bit code just didn't work. In fact, nothing, of course, hardly anything worked. But so we started off, all the codes, the first codes were 64-bit, and later as they got the hardware going, we shifted into 32. And by the time the thing was decommissioned, basically everybody was running 32-bit code, 128 PEs wide. There were some algorithms developed, which these guys can talk about. Operator splitting with Harv-Lomax and Pulliam was a big innovation. You had to split operators because that machine couldn't access more than that one dimension of a big mesh at a time on a normal code. So all of your numerical algorithms had to be splittable into factorizable so you could operate one dimension at a time. Marshall Merriam, who I think is here, came up with a real neat scheme for reducing the storage requirement for solving block tridiagonals, which occur in implicit numerical routines. And Tom Pulliam and Harv and I all worked on data management schemes. Tom and Harv, since they were doing compressible codes, they could only span one dimension of the mesh, so they could only they couldn't get in planes, so they used a scheme called pencil scheme, whereas the codes I was running were incompressible codes, fewer words per node. I could actually fit a whole plane of data, and so I operated a plane at a time. But all these codes used asynchronous I/O, double buffering, and so on and so forth, because the machine had 1 megabyte of RAM, 1 megabyte, which held everything: your code, all of your data, and the real memory then, you had to treat that as a cache, and the real memory was the disks, and so you had to do everything asynchronous to be efficient. I'm kind of hogging this. Why don't I hand this to you and let you? I got the list, but
yeah, as Bob mentioned, he wrote the really only compiler for Illiac. I would have to say the language I'm about to talk about, Vectral, was used for maybe 5% of the codes written, and CFD was used for the other 95%. But I was a young postdoc and had a lot of crazy ideas about how computer languages should look, and CFD was kind of what I would call my example of how they shouldn't look. It was like Fortran. It was a fairly ugly language, and it had to be made even uglier to map onto the Illiac hardware to prevent these inefficiencies that Bob was talking about. You could not do floating point arithmetic with simple scalars. It was just not allowed. You couldn't add A plus B in this language. Well, that's going to lessen the appeal of the machine. So, and plus, it would be nice to have things like variable dimensions and more sophisticated ideas. Now, in those days, of course, pardon? Okay. Yeah, in those days, of course, there was no common language other than Fortran, I would say, for the general group of engineers and scientists. C was somewhere in someone's mind and in a few people's microcomputers, I guess we'd call them, but not out in the world really yet. So I had the liberty, you might say, of designing my own syntax. And took it upon myself to do that, and created this language I called Vectral, because vector computing in those days was a new sexy idea, right? Vectors, this is a new concept. So I thought, well, I'll put that in the name and it'll really be great. And it seems incredibly dated now. But the language was I would say Algol-like, PO1-like, something like that, if you know what I mean. And had a modern syntax, modern control structures, implemented the same kind of asynchronous parallel I/O that the CFD language has. I really owe Bob credit for that in a little cleaner way, but basically the same ideas were there. And had the vector syntax of Illiac was the only real hardware-dependent feature in the language, I would say, and that was later on modified as we went over the craze. The language prepared us, you might say, for moving on to the craze. The hardware prepared us in certain ways, and we'll get to that a little bit later. We've got some notes on that as far as the legacy of Illiac, but I think this language kind of carried us on out of Illiac because it was born really in the dotage of that machine, and as we moved on to the craze and so on, it went on with it, with the workers, the CFD workers, and allowed them to make a fairly easy transition onto the new vector machines, which were truly vector machines rather than kind of these distributed memory SIMD machine that more characterizes Illiac. Let's see. How can I pass it on to Tom here? How about algorithms? Want to talk about some algorithms? Oh, let's see if there's anything there you recognize.
I see my name and Harv-Lomax's. As Bob and Alan mentioned, well, I should give you a little background history. I came to the CFD branch in 1974 and started working with Harv-Lomax and Joe Steger and a bunch of other people on implicit finite difference methods for solving the Euler and Navier-Stokes equations. And at that time, in 74, we were running mainly on CDC 7600. We had access, I think, from Berkeley even. We even have our own. A little bit of work on an 1800 that was sitting up in the Jim Hart's old computer lab. Then the Illiac was, at that time, in 74, 75, and 76, really not that usable for anything in terms of computations we were trying to do. The CFD language was just getting written and put together. The machine had a lot of downtime, a lot of problems, and maybe Bob or maybe even Ken could talk more about that. I always thought it was kind of interesting when you walked into building 233, which is where the Illiac was sitting. You'd go past this room and you'd see a red and green light out in front, and when the Illiac was down, that red light was spinning, and sometimes even sirens are going off. And when it was up, the green light was on. So sometimes just to check to see if you could even get a job to run, you had to go and walk down that hall and see if the lights were on, see if the machine was available. In terms of algorithms, I know Bob and Alan can talk at length about the large eddy simulation, full simulation work that was done there. People like Parvis Moen and John Kim did some really groundbreaking computations on using the Illiac at the time, getting some data which still stands as probably very useful data in turbulence modeling and analysis of fluid dynamics. So it really produced just that one result, I'd say, in terms of computational fluid dynamics and fluid physics. That particular piece of work really produced something that was useful and has been continued to be useful, and is very similar to some stuff that we're doing these days. In my own work, it was implicit finite difference techniques for solutions to the Navier-Stokes equations. And at the time, in 1978, we put together a three-dimensional code, which at the time was called AIR 3D, and it was an outgrowth of some other work. But the challenge of putting a code like that on a machine like the Illiac, where we were the first time we were really being faced with, instead of writing just serial, regular Fortran code, we're writing code that was parallel, opened up a whole bunch of research into how do you map algorithms onto machines of this class. You know, when the vector machines like the Cray came along, then it was structuring do loops. But actually, the Illiac, being, in my opinion, way ahead of its time, was where we were really thinking parallel. By the time we got our access to it, it was being handled in a very lockstep mode, 64 processor operations as an instruction. That was it. You couldn't do cross-processor. Well, you could, but we weren't allowed to do cross-processor communication. It was just load up the memory of the machine, and the machine had very little memory. It had 2,048 words of memory, and I don't know what the clock speed was, like 80 nanoseconds or...
Yeah, 12 megahertz.
Yeah. And the way we handled having a very little bit of memory to work with was we had to do a lot of work on mapping the database, figuring out how we'd put 4 million to 6 million grid points of data, or total data, I should say. The grids weren't that big at that time. Get that data into the machine, operate it on in this lockstep or this parallel mode, get some operations done, and then write it back out to the disk. And Bob mentioned he did a lot of work with Harv and myself and mapping, figuring out how to get the data off the disk, which was a big rotating drum. I think you're going to say a little bit more about that drum disk at some point? Paul would say some more about that. But it was kind of interesting. It was a big drum, and we had to figure out unique ways of mapping the data so you could bring it into the processors. We developed what Bob mentioned was a pencil database system. Other people were using planes, where you brought in just a chunk of the data, and you worked on it. And some of the concepts, like bringing in data, working on it in one direction, required us to change the way we do in our algorithms. And as Bob mentioned also, Marshall Merriam came up with something that Harv Lomax called the Marshall Plan. I was just reading in this article that Harv and I wrote a number of years ago, and it made me laugh to remember that he had that name for it. But it was where we had to change the algorithm. Part of the algorithm requires us to do tridiagonal inversions, which require you to do a forward sweep and a backward sweep of the data. And as you're doing the forward sweep, you have to save a lot of information. Well, we didn't have enough memory in the machine to do that. So Marshall got pretty innovative and said, well, we can save maybe every 10th piece of this data, and maybe the last 10, and then write a back sweep recursion algorithm that back sweep 10 and then jumped up and back sweep 10, created 10 more elements and back sweeped again. So those type of things were required 1978, 1979, 1980 to program on a machine like this. And actually, we're looking these days on the parallel computers we're using today at very similar type of concepts. Mapping the data is a big part of putting things onto computers, parallel computers. Transposes, where you bring data in, you have to turn it to get in the right direction. Or we're constantly thinking that we may have to go back to those things. So Illiac was really a machine that was way ahead of its time in that category. We were getting on the order of 20 megaflops in 1980, which is pretty good compared to what you could get on a machine now. Now I have a machine on my desk which gets like 34 megabytes and has, 128 megabytes of memory and everything else. So we've come an awful long way. But the Illiac was really a machine that was unique at the time, allowed us to solve some problems. We actually did some computational fluid dynamics problems. Steve Dyrwood, which I don't think he's here, but Steve's retired. Kind of interesting story about him was he was working on algorithms on just 2 dimensions, and one person we haven't mentioned, which is Dean Chapman, who passed away a couple of years ago, was very instrumental in getting us to put our CFD algorithms onto Illiac. And I remember him coming into Steve Dyrwood's office one day, and he was division chief at the time, and or maybe he was director, I can't remember. He might have been division director, yeah, because Vic Peterson was division chief. And Steve Dyrwood coming out, hanging his head after that, saying, I got to work on the Illiac now, I just got my marching orders. But actually, he was able to produce a very good piece of work on some boat tail computations. And so, again, the machine produced data and produced some CFD results, which were way ahead of its time, and made that machine really a precursor to everything that we're trying to do today in parallelization. And I think I'll pass it on to Ken for some more.
I'm going to sort of switch gears and talk a little bit about some of the hardware aspects. At the time, this was really avant-garde. It had 256-bit ECL memory chips. It's one of the first machines that had those. If you look at some of the PE units back there, you see they actually used welding cable to bring the power to those chips. The logic chips had somewhere between 7 and 12 gates per chip. One of the big mistakes we found is if you epoxy encapsulate these things, they really can't absorb water, and that causes problems. This was a huge machine. It was about 65 feet long, 12 feet wide. I always referred to it as Ames's 6th largest wind tunnel, because literally you had this 65 feet by 12 feet blowing up past all the PEs and the control units, past these 300-pound power supplies with special forklift things to take them out. And this was a real power pig. It used 1/4 of a megawatt for its electronics, 1/4 of a megawatt for its cooling, and you had 3 PDP-10s, a B6700, and about 36 PDP-11s, and the lighting used another 1/4 of a megawatt. So the facility was a 3/4 of a megawatt facility. We originally tried a concept of doing...
What? Can you give me an idea what that meant? Is that almost what Diablo puts out?
Oh, no.
Is that 2 megawatts down there?
No, we have a lot more than that. We have wind tunnels here at Ames that on startup will pull 100 megawatts. But you have to remember that Ames Research Center is essentially the largest power user in Northern California. And we have to work with PG&E to make sure our big wind tunnels only get turned on with only so many of them on at any one time. So even though by household standards Illiac-IV was a pig, by our wind tunnel standards it wasn't that bad.
How much is that 3/4 of a megawatt in terms of powerhouse? I don't conceptualize that.
It's thousands of homes, many thousands of homes. But I don't...
Typical power plant, a large power plant, some people.
Yeah. The early Cray 1s were, by the time you include all the heating and cooling and stuff, those were around 200 megawatts. Kilowatts, excuse me, not megawatts. I'm way out. Yeah.
The megawatt is produced by the very largest wind tunnels, the very largest windmills.
Were there any exotic problems with metallurgy and stuff to be able to cool the Illiac the way Seymour described it?
No, it was just brute force wind circulation. There was nothing exotic. I think some of the exotic things that you would see is on those control unit boards. There were 24-inch square boards with 24 layers, and they basically used a B6500 for a couple years to lay out all the boards that went into that control unit. I was talking about diagnosing the machine. Our original concept was we had what we called an exerciser, which was a PDP-8, and we were supposed to take the PE out and stick it in this little cabinet, and this thing was supposed to diagnose the hardware faults. That never really worked out. We actually did regression testing, but we also used real-life CFD codes to try to debug the hardware. One of our big problems is we got the hardware with no as-built specs. We tried to deal with that for about 2.5, 3 years. Finally said this isn't working. Shut the machine down for about 6 months to try to get a set of as-built specs so that we had a chance to keep the machine going. The logical drum they were talking about were really these 4-foot diameter discs, and there is one back there. They had 1024 fixed heads on those discs, and that's how we could get a fairly decent transfer rate out of them. But you had to be very careful about laying out your data on the right tracks and skipping patterns and so on. Towards the end of the life of the Illiac, we started having bearing problems. Now you can imagine the force that you have with a 4-foot diameter aluminum disc rotating at 3,600 RPM. And so that caused us some concern. We had head crashes. We went out and actually tried to find if anybody could resurface a disc like that. Needless to say, nobody could. But luckily the discs sort of lasted until we turned the machine off. And that's an interesting story in itself. We shut down the machine, and we had brought up our Cray 1S, and we were dismantling it. And a photographer and an author for National Geographic came around. And I couldn't understand it. This guy had been to Livermore and to Los Alamos, but he was just ecstatic because nobody would ever tell them what happened to old computers. And here is this floor littered with pallets of cable stacked up, ready to go to the recycler. And the picture he liked the best is we had one of our guys up in the rack with a cutting torch cutting the chassis apart. So with that, I'll let him go back to software.
And you once said you, when the Illiac went away, that you were going to take one of those discs and make a coffee table out of it. Did you ever?
I didn't, but Dean Chapman did.
Really?
He had a beautiful 4-foot diameter piece of like 1/4 inch or glass, even with the hole cut in the center so the hub could still stand out. Unfortunately, he took one of the discs that didn't crash, so he didn't have all those nice concentric circles that some of us have.
Well, all of this happened before Pertle showed up here?
No. Bill came with the machine. You know, Dan Slotman did the designs at Illinois, worked a lot with Fairchild to get the early emitter-coupled logic and emitter-coupled memories, because those were Fairchild memories. And Mel, I don't know, first 6, 7 years of the life of the machine, he was in charge of running it until at one point he had a run-in with Hans Mark, the center director, and they parted ways.
Well, maybe we should work our way down the list a little more then, and then we'll start. If you guys get tired, let us know. We could probably talk about this for a week. You know, it's old times. So we talked about some algorithms. I'm going to run down a list of some of the production codes that were actually run on the machine, and these are not codes that do research to see how well parallel machines work or anything. These are just fluid mechanicians and astronomers and people who just want their answers, and they want the fastest machine they can get their hands on, and they're willing to put up with Illiac in order to get their answers. The first code that actually ran, first one of our codes actually that ran on the machine was written by Walt Reinhardt and Bill Davy, and it did the simulation of the supersonic flow around the front end of the space shuttle. At that time, they were worried about the space shuttle heating on reentry, and they needed some real gas dynamic simulations of it. And that was the very first code, and I believe that code was actually running on the machine before the machine was released to the public. I mean, it was not very stable at all. And in fact, it was so unstable that instead of running the code 64 PEs wide, they replicated the code 3 times, 21 PEs wide each. At the end of every step, they would take a vote. If all 3 sets agreed, then they would proceed, they would log that step and go on. If 2 agreed, they'd correct the bad guy and go on. And if none of them agreed, they would back up and do the step again. let's see, so that was the first code, and then I'm going to go down some of these codes, and these are not necessarily in chronological order. The second code I'm going to mention is written by Parviz Moy and John Kim, and I know Parviz is here. Raise your hand, Parviz. Guilty as charged. That code I would say, was probably the heaviest used code in the world on Illiac. Certainly the heaviest at Ames, and Ames was by far the heaviest user of the machine. So that code spent more time on it. They hogged that machine. And of all the people that ran Illiac, the only person I can think of that truly loved that machine as a computer to get numbers off of was Parviz. I mean, and in fact, that was the code that was running the day that the guy showed up with the bolt cutters that Ken told you about, and Parviz tried to hold them away from that machine. They were running up to the very last minute. In fact, you got them to postpone the shutdown a little bit, didn't you?
We did 2 days. I also have one of those coffee tables. Mine actually has my data on it.
Good.
Permanently, yeah.
Well, Alan and I each have a coffee table too. Do you have one? No. Yeah, I think most of it. In fact, that was kind of funny. You should have seen the people streaming out of that building with 3-foot diameter discs under their arm. I think Marcy Smith took one, and a story I got was that a government auditor came through later. They had to inventory this stuff and checking serial numbers.
There were no NASA tags on them. So we just figured it would.
We were careful about the serial numbers. We had 70 processors. We had the 64 and some spares. And somehow or other, we were sending them off to the Navy surplus yard for scrap metal purchases. We didn't do a good job of keeping track of 4 or 5 of these processing lines. Well, the GAO, after this all got through, took the price of the Illiac-IV, divided it by 70, multiplied it by 5, and said we lost that much equipment. This was 10 years after we got it.
Now, I understand that they were kind of upset when they went in there and found that all the disc platters were gone, and nobody knew where they went, but we have a few of them. Okay, going down the list of codes, Tom Pulliam, Harv Lomax, Yvonne Schaefer, and Marshall Merriam worked on both 2- and 3-dimensional, I guess they were ideal gas compressible, compressible full Navier Stokes. I did incompressible homogeneous turbulence. Alan here did all kinds of stuff. He got to make this list up. I see his name's down here more often than anybody else. He did incompressible boundary layer transition, compressible isotropic turbulence, compressible turbulent jet and its generated noise field, supersonic base heating for the Galileo Jupiter probe. Tony Leonard, who's now a professor at Caltech, did incompressible boundary layer transition using a vortex method, which is kind of like an N-body. Instead of gravitational attractions, there are vortices in 3D. That was kind of an interesting little code, and actually I was the one who wrote the code for Tony, but that code is so computational, it's an order n² computation. It's so computationally intensive that we tied up the machine without ever going to the disk. We could run in core. And one day one of the techs over there he said, I was just curious about how many idle cycles the fence queue had. That was the queue of instructions that went into the PEs. So he said, I put a scope on one of the PEs, and there was no idle time at all for an hour. And he came over to me and he said, man, you wrote a damn good compiler. Well, it just turns out that this was the one code that didn't ever go to the disk. So yeah, that was kind of a kick. Well, I had to fess up to him that it wasn't the compiler. Bill Feiereisen, is Bill here? He's not here. He did his PhD thesis on that machine at Stanford on compressible shear turbulence. Another PhD thesis was Abraham Shirani, who did incompressible shear turbulence. And there was another fellow who was in here early who did not run on the machine, and he was supposed to. That was Bob Clark, but he came in too early, and the machine didn't come up. And finally, he talked him into letting him run his job on the 7600 so he could get his PhD and get back to work, you know. Steve Dywert did compressible aerodynamics. Dick Miller, I lost you right there, did galaxy dynamics, gravitational n-body problem. Is that right, Dick? And I think that was with Bruce Smith, and Margaret Covert helped out on that. There was a fellow named Anjay Poharil, and I don't know if Anjay is here or not. This was a an interesting code because it was the second code that used Vectral. And Anjay was a postdoc in life science, and he was doing a molecular structure calculation. And he came over to, I probably ought to let Alan tell this since this is a Vectral story, but I'll tell it and then he can give you what really happened. But Andrew came over and they worked together and he coded that thing up in Vectral. He couldn't have done it in CFD. It was too complicated, really. And when he ran it, he was very disappointed in the execution speed. It turned out it was only twice the speed of a 7600. And it turns out that 1% of his code was scalar. And that 1% killed him. He ran into Amdahl's law, and then half of his computer time was spent in the 1% of that code that was scalar. That was the only case of any of these codes that was run in Air Branch where we hit Amdahl's law at all. My joke was that in my code, the only scalar arithmetic was time equals time plus delta time. Everything else was vector. And that was pretty much true of the codes. They were absolutely parallel, no scalar code. Satellite image processing was done by Buzz Sly. I don't know if Buzz is here. He's still at Ames. He coded that all in assembly, and that did analysis of satellite image, photographic images. He was not part of Air Branch. Okay, I'm going to turn it over and let Alan talk about some of the legacy.
Legacy. Illiac was shut down after 7 or 8 years, I guess, of generating heat, maybe 5 years of generating useful numbers.
About 9.
9 years of generating heat. But I think its legacy is still with us, really, particularly in the CFD community. Tom touched on this a little bit when he was talking. But as I mentioned when I was speaking a few minutes ago, this was a vector machine, a new idea. And as soon as craze came along, hey, we can handle vectors. The rest of the world, I remember going to a meeting at Los Alamos around 1980, and they were all scratching their heads over what can we do about vectorization, and craze were these funny machines, and vectorizing compilers are a big problem and didn't do things right. But we were very familiar with that, and so that allowed us to move on to the craze in a big way right away. The other thing we were very familiar with was small memories. Hey, we had a 1 megabyte machine. When a 1 megaword machine came along, we were really happy, but that still wasn't big enough to hold the CFD database. We could use the Cray disks. We could use asynchronous I/O just as we had done on the Illiac. We were all familiar with that and ready to use it. So I think that part of the legacy was to accelerate CFD at Ames. It gave us a head start that lasted well beyond the time when Illiac was turned off. Another concept that's even more modern, and maybe its effects still are being felt now, is here was a machine with 1 megabyte of memory, which we can think of as a cache. Right? It had a very slow, or much slower, the ratio of the speeds is the relevant thing here, disk main memory. Just like modern processors, they have kind of slow DRAM, right? Very fast statogram caches. It's really the same sort of thing. The ratio of the sizes is not so dissimilar. The ratio of the speeds is really fairly familiar to those who in this audience. I'm sure a lot of you are used to those kind of problems. Let's see. Well, the SIMD architecture of the Illiac, I think, was something that troubled a lot of people while the machine was being designed, certainly, while theoretical computer science people were thinking about this possible design of a machine. But when it came to CFD, hey, it didn't turn out to be a problem, really. Tom can maybe elaborate a little bit, but except for boundary conditions, these codes were embarrassingly parallel or vectorizable. And as a result, I think all the worries about how we can vectorize these scalar codes that we've got and whether we need to do a lot of serious theoretical research in computer science in order to make them run efficiently, it just didn't apply to CFD. It probably would have applied to a lot of other fields, but as it turned out, at Ames, CFD was the main set of users, and for us, SIMD was easy. Now, the Illiac was a one-of-a-kind machine. I think we're all thankful for that in some ways. But as it was going away, or in its last few years, there was this little project started by Ron Bailey called the NAS project, originally in ASP, now in AS, as we all know and love. One of the original proposals for that project was to build another one-of-a-kind machine to do CFD. Hey, this is a great idea. Look how well Illiac is doing. Wait a minute. How well it's doing? No, I think maybe we should look at a commodity machine rather than a one-of-a-kind machine. And I think that one of Illiac's legacies was, in the negative sense, to help the NAS project move forward by not going with a unique machine, but going with an off-the-shelf machine.
We did spend a couple $1 million for erosion control data doing studies. What really convinced us when their bids came back and both of them were more than $200 million.
We actually gave them copies of vector code to take a look at, and they were working with things like the transpose, as I mentioned. I'll maybe say a little bit more about that in a few minutes when Alan's finished. So the vendors that were trying to build those computers were looking at the Illiac as their model, and maybe that's why it got to be so expensive.
Yeah, right, exactly. Let's see. Another thing about Illiac, as the four of us, particularly Bob, is an example of, is the in-house expertise that we had available. Well, that was really nice. All the software was written by people, in an office nearby. The hardware people were all over in the next building. And I think that led to a lot of productivity. I'm not sure really that's a legacy, but that's kind of an aside to the legacy issue. It's too bad we don't have that nowadays, I guess. The remoteness of the vendor software and the vendor hardware and so on sometimes is an impediment to progress. The real legacy, as far as CFD certainly, as far as physics, is that Illiac was the first computer capable of establishing an important fact about computational simulation of physical systems. In case of turbulence, the optimists were saying, yes, we will someday be able to, or we're right on the verge of being able to actually do turbulence experiments and get turbulence statistics that are reliable and physically meaningful off of a computing device. The naysayers were always saying, oh, no, you've got to use wind tunnels, we've got to stay with the experiments. Illiac was the first machine, big enough, fast enough, and with a dedicated set of users that could deal with its complexities and strangenesses, that could establish that, yes, we can do simulations of this very complex, still not understood physical phenomenon of turbulence and on a computer, and have it mean something, have it be real, and have it be equivalent to experiments. We're still, of course, at much lower Reynolds numbers than many experiments and many engineering-type systems. But we could do things on a computer that many people thought were certainly impossible at that era, and we're looking to maybe in the next century. But we did it in 1980. And that's, to me, that's its greatest legacy.
I'll be kind of brief because I think Bob and Alan and Ken have covered most of the information. I will bring us back a little bit into the early days just for a second, just to acknowledge one person who can't be here tonight, which is Harvard Lomax, who was my mentor, and Parviz and all of us our mentors. He started the CFD branch, brought together a whole bunch of really innovative and smart young scientists, and put us all together and gave us a whole bunch of challenges in both computational fluid dynamics and fluid physics and computers. He wasn't a computer scientist. His strength was in mathematics and aerodynamics and fluid mechanics. But he took on the challenge at those days of actually programming the Illiac and worked with me very closely on some of these issues of how to map these codes onto these computers. And I remember sitting with him many times in his office, running down the Bobs to try to figure out what was going wrong with the mapping or what was going wrong with one of the codes. And he really inspired people like Parviz and Alan and myself and Ken and everybody else to put these things together and make it into a very usable product, which was the final end result that Alan mentioned, which was some real good science and real good physics coming out of a machine that, at least my impression when I first got involved with it, was more of an experimental idea to see if this idea of parallel computing was going to work. Now we hear it every day. I mean, everything that you hear is parallel computing in one form or another, whether it's SIMD or message passing with multiple instruction stuff, or it's computers with lots of memory or connection machines. A lot of the techniques and a lot of the ideas that were developed in those early days are still what the vendors and what the people writing these compilers and working with the algorithms and codes are still dealing with on a day-to-day basis. So it was really our training ground. Illiac left us that real legacy of giving us that initial look into the future of how computation was going to be done. And as I mentioned before, a lot of the techniques that we developed and looked at are constantly resurfacing as possibilities, mapping the data in certain ways. Message passing on conventional machines is one of the biggest hang-ups. Right now, cache is a big hang-up. It's, again, a memory problem. You got local memory hierarchies that are making it difficult to get these machines to get the optimal speeds for the algorithms. We're also going to look at new ways of doing the algorithms. The little thing we mentioned about the Marshall Plan was Harv Lomax's saying, we've got to put this on here. We've got to feed this small amount of memory and these fast processors with the data, but we can't store it all, so let's come up with a way to figure out how to get around that. And that's why we came up with some innovative ways to do that. People are currently doing very similar things. And so that legacy of like I say, that training ground of the Illiac has got us, I think, to where we are today. And without it, we would probably get here, but I think we would have got here by a different route, and probably, in my opinion, not as good a route as we were able to follow to get here today. I'll pass it on to Ken.
One sidebar, that this whole exercise with the Illiac-IV was probably one of the first big science uses of what became the World Wide Web. You have to remember that the Illiac-IV was host 15 on the ARPANET. All of Ames Research Center was connected to host 16, so even the locals went through the ARPANET to get to this machine. And I remember coming in the mornings and seeing Steve Dywert ready to log off from Imperial College London, so it really was even the World Wide Web then.
Yeah, any questions would be appreciated.
You talked about having a dedicated group of users that actually do some of this science. One guy came out of the boss's office very hangdog because I was going to have to use it. Was there a time when there were people that chose to use the Illiac instead of being required to use it?
Oh, absolutely. There's one sitting right behind you.
Were there more than one?
Well, there weren't too many that actually, given a choice between the 7600 and the Illiac, would have taken the Illiac, but there were a number of people who wanted to do things that they knew they couldn't do on any machine other than the Illiac at Ames.
It was a very small community,
Yep.
so people were just developing new algorithms and ways of solving fluid dynamics
But there were problems that would not be tractable on the 7600.
Oh, absolutely, absolutely.
Our only competitor was the Star 100 in that time period, and there were only 4 of those built, if I remember correctly. Could we appreciate the program you did the company? Could we get an idea what the programmer visible machine architecture was?
I mean, how do we get the instructions in the machine?
On a bus, or was there weird cross connects? It was literally, you had 64 scalars that you can add and subtract, and in integer. Then you had 2048 64 word wide or 128 word wide memory configuration that you could do vector operations on, and you did have a massive data code. So, for example, turn off the boundary conditions, then turn the boundary conditions on. That was the architecture of that machine. And then you had to shuffle out to this you could shift in the ground.
We can go on to the next question.
We still have airplanes.
Processor communication, could you shift the vectors or anything?
Yeah, you could shift the vectors. It was on a torus, so you could shift one left, one right, 8 left, 8 right, and it was all end around.
That's how we did the periodic concept.
I remember reading some things that Seymour Cray talked about in terms of, I think there was an experimental parallel computer that they had to control data before you left there. And then when they were initially talking about the Cray wanted to not do parallelization, but to instead do vector operations, was there any experience that was gained from the Illiac-IV that might have, was there involved information being passed back and forth in terms of, yes, you can do vector as well, and when you program this box where everything's doing the same thing at the same time, it's easy, but if you try to do anything else, it doesn't work so well.
Well, I think, as Bob pointed out in the beginning, if you could really have distinct vectors and use a language like CFD, those were the easy things to write up, and the machine did them well. If you tried to use anything else, you had to write very contorted code, and the machine did contorted things and took a long time.
Well, I think Seymour probably saw the Illiac. If he looked at it at all, I really don't know personally whether he did or not. But if he had looked, he would have seen that, yes, the scientific codes, PDE solvers and so on, can be written for a machine with this architecture. And he would see a vector architecture as having all the same advantages, really, of this strictly parallel architecture, but also some further advantages of not losing so much efficiency when you go to shorter vectors that don't map exactly onto the natural native length and so on.
I think Seymour like the PBUs for the 7600 and the 6600, and he was looking at an MIMD architecture and sort of passing on that as opposed to the SIMD that the Illiac and Star 100 were.
Couple little history points. I want to talk about how we got here. And the other thing is, I wonder maybe you could tell us a little bit about the celluloid storage system, which I never saw except in
Unicom.
Yeah. Take it.
The original thought was ARPA was going to put it at the University of Illinois, saying as Dan Slotnick and his students were the major designers, even though Burroughs was the fabricator. But if you happen to remember, about that particular point in time, the physics laboratory at the University of Wisconsin was blown up, and I believe one student was killed. This made the Department of Defense very nervous, asked for proposals. We wrote a good proposal, but I think probably what sold us to them at that point is this was a Navy base and the Marines guard the perimeter. The Unicon was an attempt to have a very large storage device. We were thinking about strange things like you don't calculate what the weather will be, but you look up a similar situation and just figure out what it did last time it was like this. And basically what this was a machine that had rhodium strips. They were about 2.5 feet long, maybe 4 inches wide. And the mylar covered with rhodium. And the idea was they would mechanically extract these from containers, wrap them around a drum, and then use an intense laser to oxidize or vaporize the rhodium, and then a less intense laser after it had been written to get a read-write signal. The concept was perfect, but the lasers would stay in a line for maybe 24 hours if we were lucky, and then we had to call in people like Ray Lim, who were sort of, gurus or magicians that could realign this laser after a great deal of activity. So it was another interesting part to the thing that never saw commercial side.
almost like a precursor to the CD.
It definitely was a precursor to the CD and the other types of optical discs that we're seeing now. But
It was never used in production.
no, I think the moral of the story is you don't really want to end up with that kind of media that you try to register with that crude of optics, because what you can get in your CD player today is 25 years better, and that means much, much better. One of the things we called was the fixed mobile experiment, and this was one of the early times when they would actually go out and drag a long array of sonars, and we were actually trying to do real-time processing. And one anecdotal example I have that it was a success is it was out there doing the experiment, we were doing the processing, and we said, there's a submarine out there. Well, the P-3 jockeys that used to fly the subchasers in and out of here, they couldn't believe that, but their admiral ordered them to go out and drop one of their buoys, and there was a submarine out there. But then they moved it to San Diego and started using real computers instead of the Illiac-IV, because to switch from red to black, it was like a 5-6 hour read-write cycle to purge all the disks and all that sort of nonsense. So, yeah.
Secure guns control.
Just like to get you guys' perspective on the notion that you read the computer science literature today, one might construe that man was not meant to see. And I don't know if you guys would even agree with that. You're probably running your code these days on MIMD boxes, right?
A lot of them are MIMD boxes with vectors, so it's a combination.
The programmer looks like the machine produced a lot of generality.
One of the codes actually we forwarded, my wife forwarded to a mass par, one of these turbulence codes, and with 16,000 processors. So, and that was a SIMD machine. They're out of business now. Yeah.
Where do you see it going?
Oh, I don't. Well, I think the economics in terms of production of microchips and everything is going to make MEMD the winner there. Just the economics of production of the silicon.
One thing that you see happening is the microprocessor people have more and more gates that they can use. They're tending to follow the same evolution as the big iron, just to find things to do with all those gates.
And yet, one of the reasons that we give, like, I would give my students that you guys were doing SIMD back then, because it's good. It's cheap, physically cheaper than nuclear.
Look at the size of that control unit compared to the size of the PEs.
Very good. So that's the logical relative complexity. So, I mean, I work at a tester company, Xantech, and if you look at what's inside a tester, visually, it's in these computers. Even though the people in that industry are just waking up to that fact. I mean, I wouldn't be surprised if there are other computers as well. But maybe the general purpose demands something more flexible.
One advantage of MEMD that we found on Intel machines and things that we had at Ames was you could partition them and run different size partitions for different people. Some people might only need half the processors, so you could get a lot of people going at one time in various debug modes and production modes, whereas on a SIMD machine, it was all or nothing. One guy had the machine, period.
None of you mentioned bulk core memory that got added to the machine. Did that have any significance? Yeah, the systems.
I never saw it.
It never got put onto the machine. We had the big rotating disks, and we had the 256-bit ECL memories that were in the chassis of the PEs.
That was it.
The systems concepts memory never got attached?
No, we were working on it and trying to design it, and before we ever built a working board, we scrapped the machine. And that was, in fact, in answer to the fact that these disks were crashing and we could not fix them, and so we were looking at that redesign. Another redesign we were looking at is we were about at the point of we were out of spares, and we would have to redesign boards using Meckel 10K parts, and the thought of doing that was frightening.
What was the role of the PDP-10 versus the Burroughs machine?
The PDP-10 was the active front end for the processor. Mel Pirtle and his people felt it was better to try to control that with these 36 PDP-11s and 3 PDP-10s. We retained the B6700 for some diagnostics, for assembling, for using the Gleitner-Algol-based compiler, but I think we did use it for some activities with the disk subsystem, but Mel felt that the PDP-10 systems was a better active front end.
So you switched the Burroughs machine out of the control mode?
Mm-hmm.
Yeah, that's right. It in fact stayed in the room until we scrapped everything else, but it got less and less use over time. Way in the back?
You know who built the discs? Was it Microscope?
I'm not sure who actually fabricated those monsters. It was actually Burroughs.
Type 2 or whatever.
Yeah, I don't know. Okay.
Perhaps they were used on the BSP also, or is that not a contemporary decision? You're saying it's a standard?
No, the BSP was much more modern. It wouldn't have used that huge of a platter. Yeah, there were some older drums from the 60s that had masses like that. Any other questions?
I found that the internal network at the network of the Ames was kind of amusing by base standards. Every node had exactly 2 links, sort of a straight line. Had 7 machines, which is the Illiac systems.
Yeah, and we also used 300 baud acoustic modems too. We had fun. Thank you for listening.
Yeah.